Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So here we starting the topic of class 12th optics, total reflecting glass prism. Okay, what is totally reflecting glass prism? So actually this is the technique. Totally reflecting glass prism are the are the optical instrument used for giving a particular angle to the incident ray. Let us read. These are the right angled prism. Yes, these are the right angled prism. These means one of the angle equals to how much? 90 degree, which turn the light through 90 degree or 180 degree. Okay, so these are the specially designed prism that can give a turn of 90 degree or 180 degree. Okay, based on the principle of totally internally reflection. They are based on the phenomenon of total internal reflection of the light. Yes. So what happening here? Mu for a glass is 1.5, so that the critical angle for glass air interface equals to 42 degree. Students, you know that like here is a medium and light ray is coming from glass to air. And for a glass to air, the angle of critical critical angle equals to how much? 42 degree. Okay. So for 42 degree, the refracted ray will align the interface and having an angle of refraction r equals to 90 degree. But what happening when there is an angle greater than 42 degree? Let us say it is 45 degree. Now, if the angle is 45 degree, as the angle of incidence is greater than the critical angle, then according to the condition of total internal reflection, the ray will be reflected into the same medium, yes or no, and it will having same angle with the normal, as it now this ray is following the laws of reflection. So if I have incidented this ray with an angle greater than 42 degree, consider it is 45 degree, then it will travel it will travel bounce back into the same medium. Clear or not clear? So same thing happening here. In totally reflecting glass prism, angle of incidence is made 45 degree. Why 45 degree? Because 45 degree is greater than 42 degree, which is greater than the critical angle of the glass air interface, right? Glass to air, as the light has to travel from denser to rarer. So which is greater than the 45 degree. Hence the light suffers total internal reflection. Now in which way light enters total internal reflection? See here in the diagram. Like there is an object with the name AB. So 2 points are there, A and B. Now the rays incident from A. In this phase, first there is a 90 degree. You know, when a angle is 90 degree, there is no refraction takes place and light will directly enter without any deviation into the medium, right? So here is no refraction will takes place, only light will enter. Now, once the light incidented here at angle of 45 degree, the light here incidented at an angle of 45 degree, then what happened? You know, the total internal reflection will takes place, and also reflection angle is again 45 degree. So 45 plus 45 equals to 90. So the light ray is reflected here, making an angle 90 degree with the incident ray. Clear or not clear? Similarly, the bottom ray again reflected at an angle of 90 degree here. Totally internally reflection takes place. Now the image of the point A will be point here with the name A dash. An image of point B is somehow here with the name B dash. Now see what is the amount of deviation. Okay, yes. What is the amount of turning? Okay, the amount of turning here is equals to, say, previously the your object is B to A, but now it is becoming B dash A dash. Clear or not? So you see here the amount of turning is 90 degree. Clear or not clear? So you can take an advantage of turning off this light into the angle of 90 degree. So this is first application. Similarly, if you make the prism like this, then there will be two times internal reflection. So here the ray will rotate with an angle of 90 degree. Again here the ray will turn with an angle of 90. So 90 plus 90 equal to 180. So what A, the image of A will be formed here by the name A dash, and the image of B will be formed with the name of B dash. Clear or not? Now check the orientation of A, B, A and B with respect to A dash, B dash. You can observe that the image is totally inverted. Okay, this means the ray is reflected, is turned by an angle of how much? 180 degree. Clear? Yes. So in the NCRT, this topic is here. Yes, totally internally reflection. Okay, prism. These are called totally reflecting prism. Okay, so bend the light by 90 degree or 180 degree by the use of total internal reflection. Okay. Yes, done. So, students, moving to our next topic is spherical refracting surface. Okay, what are spherical refracting surface? First, try to understand a spherical reflecting surface. You have a spherical glass ball here. You have a spherical glass ball here. Okay, if you cut this glass ball like this, okay, then you have a surface is like this. Agree or not agree? As the reflector part, it is not said to be reflector, it is refractor part, not reflector. So the refractor part is convex. Yes or no? Convex means it is bulge outward. So as the reflector part is convex, so this is called spherical convex refracting surface. In the place of spherical, there will be called convex refracting surface. Convex refracting surface. Clear, beta? The center part of this refracting surface is called its pole. O. O is called pole. Clear? And the aperture is very less. Yes. For very less aperture. Yes. The aperture are very less. Clear or not clear? Yes. And there is a consideration that aperture is very less. So this is called a spherical refracting surface, and in which we have deal with the convex spherical I am saying again and again reflecting, sorry, is convex spherical refracting surface. Okay. So make a clear classification: spherical refracting surface. So there are two types of refracting surface, especially spherical refracting surface. One is concave refracting surface. Another one is convex refracting surface. Clear, beta? Concave refracting surface, check how it like. Yes, this is concave spherical refracting surface. This is called its principal axis. Optical center is lying somehow here. Okay, this is the position of pole or optical center, and focus of the concave part, it's towards its center of curvature. So if center of curvature of this surface is here, then the focus will lying somehow here. Clear or not clear? Hmm. Then after convex spherical reflecting surface, yes, this is convex spherical refracting surface. If the refracting part of a spherical surface is bulge outward, then this surface is called convex spherical refracting surface. Clear, beta? Now, there is a strong consideration we have to consider throughout the derivation of the articles related to these spherical surfaces. I am writing there. So, what is the assumption we have to take? First, sine theta is near about theta. Okay, as the angles are very small here. In the case of optics, during the optics, the angle is very small. So, for very small angle, sine theta is near about theta, and tan theta is near about theta. Clear? Sine theta is near about theta, and tan theta is near about theta. Yes. So let us start. A spherical refracting surface, a refracting surface which forms a part of a sphere. A refracting surface which forms a part of a sphere of transparent refracting material is called a spherical refracting surface. These are two types of there are two types of spherical refracting surface. One is called convex spherical refracting surface, and another one is concave spherical refracting surface. Convex spherical refracting surface. It is the convex towards the rarer medium. Yes, for convex spherical refracting surface means it is convex towards the rarer medium. This is very important. So see, the convex face of this refracting surface is towards the rarer medium. Means here the rarer medium should be present. Clear or not clear? So convex part is towards the rarer, and here it is denser. Obviously the glass will be denser. So mu1 is less than mu2. And here if this is mu1, this is mu2, then for concave spherical refracting surface, the concave part the is towards the rarer medium. Clear? The concave part is towards the rarer medium. So concave spherical refracting surface, it is the concave towards the rarer medium side. So make these two diagrams very clear in your copy. First is convex spherical refracting surface. The center point of the refracting surface is called pole. Okay, and the refracting surface is a part of a sphere. The center of that sphere is called center of curvature. Yes. So for both of them, they having center of curvature, and in the side of center of curvature, they will have a focus. Okay. Yes. So check. Now see the terminology. Make the diagram. One first is pole. Okay. So for the refracting surface, rarer medium, convex refracting surface, rarer medium is towards the convex surface, and for concave refracting surface, rarer medium is towards concave surface. Clear? For convex refracting surface, the rarer medium is towards the concave part of the surface. Okay. For concave spherical refracting surface. And for convex spherical refracting surface, the rarer medium is towards convex part of the refracting surface. Clear? Means refracting surface can be judged by the placement of rarer medium. Okay. Towards what surface your rarer medium is. Okay. This is used to judge what spherical refracting surface you have been given. Clear? Now, mid the diagram. Now, important terms. First, pole. So, what is pole? The center of spherical refracting surface is called pole. Yes, the center of spherical refracting surface is called pole. So, geometrically, there will be a center of spherical refracting surface, this one part, okay? This curvature, this curvature having some central point. So this central point of this curvature is called pole. Clear or not clear? So center of the spherical refracting surface is called pole. I am not talking about this center. I am talking about the curvature center, the center of the curvature part. Clear? So this is called pole. Okay, then next, center of curvature. Yes. So your refracting surface is a part of a sphere. Definitely, it will be a part of some sphere. So the center of that sphere from your is refracting surface is taken out. The center of that sphere is called center of curvature. The center of the sphere of which the spherical refracting surface is a part is called the center of curvature. Clear? Radius of curvature. So simple. The distance of the pole from the center of curvature is called radius of curvature. So these are called radius of curvature. Clear? Yes. Radius of the sphere of which spherical refracting surface is a part is called radius of the curvature of the surface. It is represented by r, or simply it is the distance between pole and center of curvature is called radius of curvature. Clear? Yes, but remember, if this distance is radius of curvature, then this is also radius of curvature because all the points are lying on the periphery of the circle or sphere. Clear or not? So all these lengths are what? Radius of curvature. Clear? Yes. They are also treated as normal to the surface because normal on the spherical surface is passing through the center. Clear? So these are also said to be normal. Okay? So these radius of curvature behave as a normal. Clear, beta? So pole is clear, then radius of curvature is clear. Now principal axis. What is principal axis? The line passing through the pole, the line passing through the pole and the center of curvature of the spherical refracting surface extended on the either side is called principal axis. Yes. So it is the imaginary line that is passing through the pole and center of curvature. Yes. So the imaginary line that is passing through the pole and center of curvature is called principal axis of the spherical refracting surface. Clear, beta? Now Cartesian coordinate same. The all the distances measured from the pole. First thing, all the distance are measured from the pole. Clear? Second thing, all the distance measured in the direction of incident ray of light. If your light is coming from left to right and your pole is here and you measuring your distance in the direction of incident ray, so that will be taken as positive. And the distance is traveled or measured in the direction of opposite to the direction of incident ray of light, that will be taken as negative. Understood? Same rules of sign convention are usable. Now, next very important assumption for application of a spherical refracting surface. First thing, as these curvatures are very small, then you have to calculate this distance from point P. Clear or not clear? If you draw a aperture, then there will be a point M in the line of aperture. Clear or not clear? For a small aperture, the point M is considered will be considered at P. Clear? You have to consider your point M at point P. Clear? Yes. Second consideration. So first assumption, the object consists only of a point lying on the principal axis of a spherical refracting surface. Yes. So you have to consider the object consists only of a point. Yes. In a spherical refracting surface, you have to take a point object. What type of object? Point object. Yes, lying on the principal axis. Second, the aperture of the spherical refracting surface is very small. As I said you, the aperture is very small. Okay. And when the aperture is very small, the distance from this point and this point is negligible. Means you can consider the point M on the place of point P. Clear? because this distance is very small, that is absolutely negligible. Third, the incident ray and reflected ray make a small angle with the principal axis of the surface, so if the rays are making very small angle, okay, then sine I becomes equals to I and sine I R becomes equal to R, as these angles are very small. Clear or not clear? Yes. Now, derivations, so many derivations are there. All total 6 to 8 derivations are there. Refraction from rarer to denser medium at a convex spherical refracting surface. Rarer to denser medium. First, so when your refraction is from rarer to denser, there are two categories. First is rarer to denser and second denser to rarer. Clear? First type of refraction, your object will be placed in the rarer medium. Clear? And in second variety of derivations, your object is placed on denser medium. Clear? Okay, so let us start the derivation. Refraction from the rarer to denser medium at a convex spherical refracting surface. So we have a convex spherical refracting surface. So this is a convex spherical refracting surface. This is the pole P. Okay. Now, first case, when your object is situated on rarer medium. So in first case, we have to take our object at position at point O that is situated on the rarer medium. Here the medium is mu1 and the medium inside that is denser is equals to mu2. Clear? So case number 1, when your object is real, sorry, not object, image is real, when the image is real. Yes, so let a spherical refracting surface xy separate a rarer medium of refractive index mu1 from the denser medium of refractive index mu2. Suppose the surface is convex towards the rarer medium. Obviously, that's why it is called convex spherical refracting surface. Okay. So, suppose the surface of convex, suppose the surface is convex towards the rarer side. Let P be the pole, C be the center of curvature. Okay, and R equal to PC is the radius of curvature. So we have considered all essential points. There is C, that is center of curvature. Okay, and radius, the distance from P to C is equals to R, that is called radius of curvature. Clear or not? So check here, this point is point P and that this point is C. So the distance between P to C is equals to R. Now, this is point object O. Okay. C is the center of curvature. So R equal to PC be the radius of curvature. Now, first make a ray that is incidented on this convex spherical refracting surface like this. Clear or not? So this become the object and the object distance is considered as U in the optics. So we have considered this one as U. Okay. Now what is first need for to perform your refraction? You first want a normal. So what is normal? Any ray that is passing through the center of curvature, that is called a normal. Clear or not clear? So this we have the normal. Now normal, consider the light ray, incident ray making the angle with the principal axis is alpha. Okay. So angle of incident ray made with the axis principal axis is alpha. Now second, the radius of curvature, not radius of curvature, the normal at the point of incidence making an angle gamma. Clear beta? Now check the type of refraction here. As the rays are coming from rarer medium to denser medium, the rays has to go like this. Yes, if there is no refraction, then there will be a original path. Right or wrong? This like original path. Clear or not? If there is no refraction, then the light ray will go along that its own initial direction. Yes or no? But here refraction will takes place because the light ray is coming from denser, rarer to denser, rarer to denser. Mu1 is here rarer and mu2 is here denser. Clear or not clear? And you know, when the light ray is coming from rarer to denser, it bend towards the normal. Okay. So what is the actual way of light? This will be the actual way of light. Yes or no? And this will be the angle of refraction R. Clear? It becomes bent towards the normal. Okay. So this becomes the ray diagram for your figure for your this situation. And now you have alpha, you have beta. Consider the this ray make an angle beta. Okay, what is this? This is image. Okay, this is image. Yes. And one more thing, you have to consider the first one ray that is passing through the pole. So that will the pole uh, at the pole there is an angle of incidence equals to 90 degree. So first ray pass through undeviated in the direction of principal axis. Clear or not clear? Now when the two light ray meets at any point on the principal axis, there will be an image of this point object O. So this point is I. Okay. Clear the diagram? All diagrams is clear, each and everything. Okay. Now see here, first some distances. Distance from P to O, PO is here equals to minus U because we have to move against the direction of incident ray. So PO will be negative. Clear or not? Okay. Then second, P to C, P to C is equals to radius of curvature, that will be plus R. Okay. And P to I, that is the distance of image, that will be plus V. Clear? Okay. So all the distances are there. So now, yes, a ray of light is starting from the point O and incident normally on the surface xy along OP passes through a straight line. Yes, so this is the first ray that is incident on the point P and goes undeviated because it is normal on the surface. Clear or not? First ray. Now another ray, light ray incidented on the xy. So another ray that incidented on this curvature at some point A, another ray of light incident xy along OA with an angle I. Yes, so this is angle of incidence made with a normal angle I, and this is angle of refraction R. Clear or not clear? Yes. So it refracted along AI at an angle R and bending towards the normal CAN. This is normal CAN. The two refracted rays actually meet at point I, okay, and forms the real image of point object O. And we have all three angles check. First angle, angle AOP equals to alpha, angle ACP equals to beta, and angle AIP equals to gamma. Clear? So we have the three angles, angle alpha, angle beta, angle gamma. Okay, yes, angle alpha is given here for point object O. Angle beta is this one for image, and gamma is for this center of curvature. Clear? And I and R for this, for angle of incidence and angle of refraction. Clear? So we have considered all these angle alpha, beta, gamma, I and R. Now by exterior angle theorem, in class 9th we have studied exterior angle theorem. So what is exterior angle theorem? Exterior angle theorem said that this is called exterior angle if this angle is gamma and the distant interior angles are alpha and beta, then according to theorem that gamma is equals to alpha plus beta. Okay, do you know this, students? This was the exterior angle theorem. Clear or not clear? Yes, the distant angle, distant exterior angle is the sum of the interior angles. Clear or not clear? So here check the triangles. First, we have to take the triangle AIC, IAC. Yes, IAC. This is I. This point is A and this point is C. Clear or not? So IAC, in triangle IAC, the angle gamma is equals to angle R plus beta. Gamma equals to R plus beta. Okay. Gamma is equals to R plus beta. This is angle gamma and this is equals to R plus beta. Clear or not? So in triangle IAC, I can write gamma is equals to R plus beta. So R equals to gamma minus beta. Yes or no? This you can give equation number 1, right? So first we have find that R equals to gamma minus beta. First from this triangle. So we find that R equals to gamma minus beta. Now take the another one triangle. Um, Triangle OAC. Triangle OAC. Okay. In triangle OAC, we can say here I is the exterior angle. You see this one angle is the exterior angle and two interior angles are this alpha and this angle OAC. So gamma. Clear or not clear? OAC. So I is equals to alpha plus gamma. So I equals to alpha plus gamma. Clear or not clear? So you can write I equals to alpha plus gamma. Equation number 2. Now we know refractive index as the light ray is coming from one medium, outside medium to the second medium, 1 to 2, then 1 mu 2, 1 mu 2. This is equals to mu 2 by mu 1 equals to sine I upon sine R. Clear or not clear? So 1 mu 2 equals to sine I upon sine R. Hmm. And as these angles are very small, so I said that for a small angle, theta is nearly equal to sine theta. Clear or not clear? So you can consider R as sine R and I as sine I. Okay. So sine of I, in the place of I, you have to take alpha plus gamma. Okay. Okay. So I can write here sine I for the small angle sine I. You can write sin I equals to I and for sin R equals to R. So mu 2 by mu 1 equals to I upon R. I upon R. Clear? Mu 2 upon mu 1 equals to I by R. So as I said, mu 2 by mu 1 equals to by the Snell's law sin I upon sin R. But the angles are very small. So you have placed that, sir. That this becomes I upon R. So mu 2 into R equals to mu 1 multiplied by I. Got it? Mu 1 into I equals to mu 2 R. Now place the angle here for I. As we have figured out, I equals to alpha plus R and R equals to gamma, alpha plus gamma and R equals to gamma minus beta. Yes or no? So R equals to gamma minus beta and I equals to alpha plus gamma. So we just have placed these values here. Now angles alpha, beta, and gamma are so small. And we have taken a consideration that theta is nearly equal to tan theta, and that tan theta is equals to perpendicular upon base, right? So place these values. Now check the alpha in the diagram. Check the value of alpha. Yes. See here. I'm using a blue color pen here to make you understand. Yes. See this angle is alpha. Now, if you make a perpendicular here from this position to this position, so alpha that I have considered as tan alpha. So for this angle alpha, perpendicular is equals to AM and base becomes OM, right? So it would be AM upon OM. Clear or not clear? Yes. Similarly, for angle beta, tan beta becomes again the perpendicular for it is AM and the base is here I am. Okay. And for gamma, tan gamma is equals to perpendicular AM upon base is CM. Okay. Now place all these values here in the given derivation on respective areas. So you will have mu1 AM upon OM, AM upon MC, mu2 AM upon MC minus AM upon MI. Okay, we just have put these values of alpha. In the place of alpha, we have put 10 alpha. In the place of gamma, we have put 10 gamma. Here again 10 gamma. Here again 10 beta. Clear? Now, M is very close to this point M. That perpendicular is very close to point P. As I said, the aperture is very small, so this point P is very closer to point M. So we should have take this point P is nearer to point M. So the distance OM is near about OP. Yes or no? Because point M is approachable to P, so OM equals to OP. Fine. So place there all the distances. In the place of M, you have to take P point. So this become PO, this become PC, this become PC, and this become PI. Clear? Now what? Numerators are cancelled out from AM, 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 AM. Each and every numerator getting cancelled out. Yes or no? So this become 1 upon PO plus 1 upon PC equals to mu 2 1 upon PC minus 1 upon PI. Clear? Now open these. So mu 1 upon PO, mu 1 upon PO plus mu 1 upon PC equals to mu 2 upon PC minus mu 2 upon Pi. Okay. Now you can gather this one. PC, this one. Take this one this side and take this P items leftward. So this become mu 1 upon PO plus mu 2 upon PI equals to mu 2 minus mu 1 upon PC. Fine. Now place these values. PO. What is PO? In the start of derivation, I said what is PO? PO is minus U. Yes, check here. PO equals to minus U, right? This is object distance. PC equals to plus R and PI equals to positive V. So put these values in the place of PO, PC and PI and we have the derivation mu 1 upon minus U equals to mu 2 upon V equals to mu 2 minus mu 1 upon R. Got it? So this is the required relation governing refraction from the rarer to denser medium at a convex spherical refracting surface. Clear, student? Yes, this is very important derivation. Okay, every year this has been asked for the 5 marks. So kindly do it now. You have the PDF now?